Thanks so much. Hello, everyone. Thank you for coming here for this session. Today, we want to talk about how we handle metrics instrumentation and ingestion for serverless environments at Shopify. So my name is Pedro. I work as a production engineer at Shopify, especially on the metrics team. Recently, I joined the Prometheus team as well, and I often contribute to some open source projects like Thanos, Stats the Exporter, and others. There at Shopify, I work with Philip, who is also on the observability team. Together with the team, we created a metrics platform from the ground up. Philip is also a contributor to many projects and a maintainer, actually, of Thanos, Kubestate Metrics, and others. And sadly, Philip couldn't be here presentially, so he will be joining us from our recording. So a little bit how we're going to divide our talk. So Philip will start talking about Shopify, how we do observability at Shopify, talk a bit about the production platform that we have there as well to kind of abstract away the complexity of Kubernetes, how we change this production platform to also integrate serverless workloads. Then we'll talk about some of the challenges that arose when we did this process of extending and the solution that we adopted. And I'll be also talking about learnings and some wins and the next steps for this pipeline. So without further ado, let's take it to Philip. Sorry, the audio for the video.
Like to think of ourselves as the company that powers global commerce. What we see here is what we call the Shopify Globe. That's a real-time visualization of where our merchants are located and where they're shipping their products. So we can see that we already have merchants all across the globe, which means that all of our infrastructure needs to be global, which also means that all of our observability needs to be global and globally distributed. So this obviously comes with all kinds of challenges. We have to be able to handle things like regional failures, for example, and so on. In addition to the globally distributed nature of observability, Shopify itself has been growing rapidly over the past years. What we see here is what we call our GMV for the Black Friday, Cyber Monday weekend. So this is just the total amount of sales for those weekends. And we see that this number has basically doubled between 2020 and 2024, which obviously puts a lot of strain on the platform as we have much more just commerce going, many more sales going through the platform, many more merchants, many more shoppers, which means that the infrastructure has to be has to grow, has to be more resilient, which also means that observability has to be much more robust. So in order to kind of facilitate this growth and to support Shopify's mission, we've done something that's pretty ambitious. We've built an internal observability platform, which we call Observe. The difference here is that we treat observability as an integral part of Shopify itself. So we would say that Observe is part of Shopify. The reason why we do this is so that we can actually connect a lot of Shopify-specific, domain-specific information, a lot of things that we know about Shopify itself into observability directly. So if you're kind of more interested in the broader picture, in how Observe works, how it was built, all of the things that it can do. We did a mini conference last year where we kind of did a lot of presentations on this topic, and all of the recordings are now widely available. So if you're interested, you can take a look and just follow the link on this QR code. And finally, to give you kind of a sense of scale, during last year's Black Friday, Cyber Monday weekend, at peak times, we had to ingest something like 100 gigabytes per second of just log volume, 12 million spans per second, and about 350 million stats samples per second. So these numbers, they're quite significant, and these were the numbers at peak Black Friday last year, and they're already reality today. due to the growth of the platform. So before we talk about integrating serverless into this, I just want to give a brief overview of how applications get deployed to production. For a while now, Shopify has been kind of running exclusively on Kubernetes. We're hosted in Google Cloud. And the key difference here is that engineers don't necessarily get to write Kubernetes manifests. So they write something that's called a runtime manifest. And then the production platform takes that runtime manifest, generates Kubernetes manifests, and applies them to Kubernetes and manages all of the lifecycle of the application. And during this process, we kind of wire up all of the observability. Essentially, engineers only need to worry about instrumentation, and then we make sure that those instrumentation signals get collected in whatever way we decide is appropriate. That's different, obviously, for traces, metrics, and logs, and profiles as well. But where those signals need to be sent is not the concern of the application engineer. And so about a year ago, Shopify started looking into moving certain workloads to serverless. So we're not talking about fully replacing Kubernetes, but rather extending the capabilities of the platform with serverless as well. Our main motivation was that we had a lot of hackathon projects and experimental projects that would just get forgotten and would run somewhere on the side. No one would even know that they're running, and this obviously costs money. So with serverless, we had the ability to automatically scale these workloads to 0 replicas and $0. And then the flip side of that is that if we had to serve production traffic, serverless obviously can scale up to kind of more or less, in theory, an arbitrary load. So we were ready to go if we really needed to serve production traffic. So for serverless, we also have a manifest which engineers provide. In this particular case, from this manifest, we would generate a GCP project, a Cloud Run environment. Then we would set up a domain name for the application. This application would get its own database, its own Kafka consumer, and it just would be ready to go. So this kind of deployment model is quite simple and elegant in the sense that it provides a self-contained application. But in our case, it also comes with a wide set of challenges. So to begin with, new projects, or rather every serverless project, runs basically in the Google proprietary network to which we don't necessarily have direct access. So things like scraping metrics becomes very difficult, and also pushing metrics from the application to the observability service also becomes non-trivial because now we have to go over the public internet, for example. We also don't have access to the underlying node, so a lot of the aggregation patterns that we use to aggregate logs, metrics, and so forth are simply not feasible in this environment. And finally, application instances can be just evicted and terminated at any point in time. So whatever aggregation we do in the application has to be done very carefully and so that we don't necessarily lose data. So with that in mind, I'll now hand it off to Pedro to kind of walk you through the solution and architecture that we put in place for instrumenting serverless applications.
All right. So as you saw, we were left in a point where we had to tackle these challenges from the serverless extension of the production platform, basically in 3 categories: instrumentation, and so how we managed to move some of the applications that were running Kubernetes already having their instrumentation set up, or also at the same time adopt new projects and having them bring their own instrumentation. Then the problem of bridging the networking gap between the existing, the new projects that were set up in not peered networks, and how we would ship these metrics across the projects, and the ingestion into our existing metrics pipeline. So before we continue and talk about instrumentation, a quick review of statsd. At Shopify, we are Ruby shop, and by default, we use statsd as our default instrumentation. Statsd, on one hand, can be very good, very simple. It's a text-based protocol. It's usually very light on resources for the client and sent via UDP, but can also be quite verbose, as we can see here, for a single application where we're sending this statsd sample. If the application is receiving 1,000 requests per second, it will be producing about 6.5 megabytes of only statsd data. So it's very important to have aggregation on the client side. And so we wanted to allow existing Ruby apps to keep sending data the way that they were used to, which is statsd, but also push the new services written in other languages to use OpenTelemetry. And so the OpenTelemetry allowed us to do that, but with some limitations, because at the moment when we started this work at version 0.84 of the OpenTelemetry collector contrib, it didn't have support for the dog.statsd format that we used. So we had to leverage this OTel collector builder to build our own distribution of the OTel collector, where we forked the statsd receiver here and replaced it with our own implementation. Now we are using the upstream version because these changes have actually been incorporated into the upstream version. So once we had decided that we needed to use both, we had to use the OTel collector. We wanted to move in that direction, but we didn't know how. And that was when we talked with Google, our cloud provider, and we opted in for a new feature for the sidecars that they have. And these would allow us to basically run the OTel collector as a sidecar to the application and send both statsd traffic on the loopback as UDP, but also send OTLP also via the loopback interface, and then ship outside of the project through the public internet OTLP using protobuf plus compression, which is much more efficient than sending all of these statsd samples. So we landed on this architecture at the end, where we have applications running on Cloud Run here. They are sending metrics to the sidecar, as I said, either via statsd or OTLP. Then the work of the collector here is to batch the metrics together and also do some aggregation, and then send these batch metrics through a public ingress, because, as we said, we don't have peering between those projects, so they have to send the information via the public network. And once these metrics get into our clusters, we reuse this metric router that we have. I will get into more details about that in a second. And this metric router will forward the metrics through statsd exporters to Prometheus. For traces, it's a much simpler step. So we send also traces from the sidecar, and it will go through the public ingress into a set of OTel collectors that are running inside the observability cluster and into the trace storage. Okay, so if you were paying attention until now, you may have heard that we have this step where we send metrics from this metric router to a set of statsd exporters, and you may wonder, like, what are these guys doing? So there is a step here of conversion between OTLP to statsd. And I have to explain this a little better. So at Shopify, inside our Kubernetes workloads, we already are using statsd, and this metric router is also used within our clusters to process metrics and also work very tightly with our observe platform to control cardinality and by dropping some certain labels, etc. So we had done a lot of work to tightly integrate this metric router with our platform, and so we wanted to build on top of that work. And so we leveraged some of open source libraries, like the OpenTelemetry mapping Go from Datadog, which maps OpenTelemetry format data to some custom memory formats and structures. And the most important here being the mapping between exponential histograms in OTLP to DD sketches. DD sketch is a in-memory structure that allows you to aggregate histograms from different sources into one single structure, basically. If you want to understand more about our custom metric pipeline inside the clusters and the collection, we gave this talk at PromCon 2023, me and Philip, so you can take a look as well. And if we take a step backwards then and talk about the configuration of the sidecar, this is what it looks like. So for traces, you have simple pipeline where you have traces being ingested as OTLP. Then you pass through a step of resource detection to check where the traces are coming from and gather all this information about the cloud environment that is the application is being run. Pass through some transformation steps to remove some of secret data that we may have there in the traces, and batching and then sending over to OTLP as well. For metrics, you have both entries, so either OTLP or statsd. Then you also pass through a step of resource detection, forwards these metrics to this resource step where we map some of the resource attributes into metric attributes, because we discard most of the resource attributes, otherwise we would have problems with cardinality. Then we also, and then the most important step here on the configuration for us is this processor of cumulative to delta, where we need delta temporality later on when we are converting the metrics inside the observability cluster. And so we need to make sure that all metrics that are being shipped to us are in the delta temporality, otherwise we'll lose the information. Yeah, so once we deploy this, of course, at day 2 of operations, we saw some problems, and we had to solve them. We saw that some clients were losing metrics here and there. And in serverless, the main thing is that really everything is preemptible, and you may end up losing data if you don't configure your observability workloads properly. So we had to reduce a lot the flushing interval of the hotel collector. Also, in Cloud Run, you just get 10 seconds of grace period, and it's not configurable. So if you don't flush when the container receives a seek term, if you don't flush in 10 seconds, you will lose everything that is in transit, in memory. And also, we had to set up really good ordering of the containers to make sure that the application didn't go up and started serving traffic before the hotel collector was ready to receive metrics and traces. Some of the wins that we had and things that we really found critical to the success of the project was leaning on the platform that we already had to auto-configure all those parts of secrets, management, and how to communicate between the projects. This was really good, and having all this automation resulted in a much better developer experience, where they had the same thing as they had previously in Kubernetes, where they just deploy their application and just worried about how they write their code and getting the applications up online, and don't need to worry about this infrastructure side. Yeah, so some of the next steps we want to tackle in our pipeline is to also handle logging. We have a custom logging platform inside Observe, and we want to send our logs from Cloud Run there as well to have better visibility into all the signals. Also, we want to set up some self-serve authentication via MTLS. Right now, we are using basic authentication, and can get quite messy, so we want to improve that. Another step we were considering is that we have this metric router today, and the only reason that we are converting actually to another metric format that is stats inside the cluster is that because we have the cardinality control implemented inside this metric router, but we could also do the same directly on the OTL collector, which would allow us to simply remote write these metrics afterwards to our Prometheus-enabled servers. And the last thing is that so far we've been using a lot of auto-scaling, used eventing-based scaling with KEDA in our backend, and this has been working well, even with Black Friday, for example. But it would be good for us to have some persistent queues during the whole pipeline to handle back pressure a little bit more. Yeah, that was it for the talk. If you guys have any questions, I'm also open to questions. The microphone is there on the stand. And yeah, thank you so much.
Hello, thanks for the talk. I have a question. You just mentioned about adding cardinality control into the collector contrib. That's a really interesting idea to me, so I want to hear a bit more about how you intend to do that.
Sure. So right now, the OpenTelemetry collector has this transformation language where you can drop or change the metrics as you see fit. So the idea here, and what we actually do already, is basically from a set of metrics, we want to keep just label ABC. So if you see a metric sample coming in that has other labels other than that, you drop all these other labels, and the hotel collector itself will take care of doing the aggregation for you, and afterwards sending just the metrics without those labels. And this will effectively implement cardinality control for you.
I see. So does it have to be a delta metric for that to work, or can you do that in cumulative as well?
No, you can also, it should also work with cumulative. In this case here, the temporality, it doesn't really matter because it will just be like how you will send the metrics at the end of the pipeline, basically.
Okay, all right, thank you.
Okay. Thank you for the talk, Pedro. If anyone else wants to run to the microphone for one more question, then you have 3 seconds. Okay, it seems we have no more questions, so thank you for the talk, Pedro.